Okay, hello everyone. I'm Takagi from Chuo University in Japan. At first, I was going to join the session of the impact and dynamics, but this session was postponed and I suddenly joined this session. So please note that the contents of my presentation is maybe a little different of this session table. Oh, sorry. But it's a great honor to join this session. So today I'd like to talking about loading rate dependency of mode 1 fracture strengths of epoxy adhesive joints evaluated by Shpb and laser shockwave adhesion test. Let me begin by talking about introduction. First, I'd like to explain the background. In transportation and aerospace industry, reducing the aircraft structural weight and simplifying the manufacturing process are strongly demanded. To achieve this, adhesive bonding is attractive a lot of attention for fastener-less structure. However, adhesive bonding is not yet in practical use because of insufficient evaluation of strength reliability. One of the reasons for the difficulty in strength reliability is an existence of strain rate dependency in mechanical properties such as yield strength, fracture strength, and deformation stiffness of an adhesive. So therefore, it is expected that the bonding strength of adhesive joints also exhibits a loading rate dependence. So evaluation of bonding strength at a high loading rate is important. So as a method at very high loading rate, we have developed and utilized new experimental method, LASAT, LASAT. In the next slide, I'll introduce LASAT. Here is an overview of LASAT. LASAT stands for Laser Shockwave Adhesion Test. LASAT utilizes a high-speed and powerful shock wave generated by laser ablation. LASAT uses a pulsed energy laser as a driving force. This is a close-up view of the specimen parts. As a specimen, ring-bodied adhesive on the substrate surface. And EA layer is responsible for generating plasma pressure through ablation. And this study used silicon oil-based viscous fluid. In order to keep constant the thickness of EA layer, sapphire glass is arranged. First step of LASAT, the pulsed energy laser was irradiated to EA layer. Then by EA layer absorbing the light energy, it rapidly expands in volume and vanishes. And this is laser ablation. Due to laser ablation, plasma pressure is applied and compressive shock wave is generated. When this shock wave propagates through the specimen, when it reaches the opposite free surface by free end reflection, compressive shock wave turns into tensile shock wave. At this time, the arrival of the shock wave causes the free surface of the specimen to vibrate slightly. The vibration velocity out of plane velocity was measured by PDV. And finally, after this wave propagates through the interface again, the delamination occurs. The delamination was observed directly in real time using a digital microscope. This is an actual laser ablation. Now let me explain the purpose of this study. In this study, we evaluated and clarified loading rate dependency of mode 1 fracture characteristics of adhesive joints. We investigated two kinds of characteristics, A, fracture strength, B, fracture toughness. And this study conducted three kinds of experimental methods over a wide range of loading rates: tensor test, SHPB tests, and LASAT. Next, I'd like to talk about mode 1 fracture strength. First of all, we conducted razors. As a specimen on the top surface of a mirror polished aluminum alloy, epoxy resin adhesive was cured with 100 micrometer at room temperature for 2 days. In razors, we determine the critical laser energy. Critical laser energy is minimum laser energy of generating delamination, and it is corresponding to the bonding strength. As a result, we determined the critical laser energy was 350 millijoule. And at this energy, we observed interfacial delamination as shown in this figure. In order to evaluate bonding strength quantitatively, we conducted FEM simulation. This is a detail of a FEM model. On the bottom surface of this model, plasma pressure of laser ablation was applied. This pressure history was estimated by inverse analysis using Fourier response function. This is a wave propagation behavior of FEM. The contour map displays stress component of Z direction. First, at the beginning of propagation, compressive wave was generated. Then, when this wave reaches the free surface of FEM model by free end reflection, this wave turned into tensor wave. This behavior of FEM was similar to that of explained in the overview of razors. Then we obtain the interfacial stress at this model of the center. This study defines the peak value as the bonding strength of adhesive joints. So the fracture strength of razors was determined as 116.3 megapascal. And next, to evaluate the loading rate dependency, we conducted SHPB test. SHPB test is commonly conducted as a dynamic loading test. This is an experimental example of the strain response sheets of incident and transmitted bars. If dynamic equilibrium was satisfied, the nominal stress and nominal strain of epoxy resin layer were calculated by these equations. As a result, bonding strength of SHPB was defined as about 40 megapascal, and fracture morphology was cohesive failure. In addition, we conducted quasi-static tensor test. As a result, in tensor test, bonding strength was determined as about 14 megapascal, and fracture morphology was cohesive failure. This is a relationship between loading rate and mode 1 fracture strength. Fracture strength was significantly dependent on the loading rate. Compared with SHPB test and tensor test, fracture morphologies were same. It indicates that the tensor strength of epoxy resin increases as loading rate increases. On the other hand, compared with razors and SHPB tests, fracture morphologies were different. It indicates that as the loading rate increases further than the SHPB tests, the strength of epoxy resin itself increases too much and it exceeds the interfacial strength. So therefore, this increasing tendency was due to loading rate dependence of the tensile strength of the epoxy resin itself. From this slide, I'd like to talk about mode 1 fracture toughness. To evaluate impact of fracture toughness, we conducted razor crack extension test. This is the experimental procedure. At first shot, we generate an interfacial delamination and measure initial crack diameter, DI. And then we continue to razor with bigger laser energy and bigger irradiation diameter. And we measured the extended crack diameter, DE. And using DI and DE, we calculated the amount of crack propagation, delta A. This is an experimental result due to scan shots. We observed delamination was clearly extended. As a result, we calculated the amount of crack propagation as about 200 micrometer. In order to determine the impact of fracture toughness from laser crack extension test, we conducted FEM simulation with initial crack and CGM. This study used exponential traction separation law like this. Other analytical conditions were same as before. This is an example of FM result, wave propagation behavior and crack propagation behavior. As shown in this animation, we observed cracks started to propagate as the opening displacement increases due to tensile stress wave. In order to determine impact of fracture toughness, we explored sustainable energy release rates that could reproduce the experimental results. This graph is the relationship between energy release rate GC and the amount of crack propagation obtained by FEM. According to this figure, we could determine the impact of fracture toughness as 185 joule per square meter. In addition, we conducted planche-static DCB tests. DCB test. This is an example of force displacement curve obtained DCB test. And using this curve and this equation, we determined G1C was 115 joule per square meter. So this is a relationship between loading rates and mode 1 fracture toughness. Mode 1 fracture toughness mode 1 fracture toughness increased depending on the loading rate. But this is caused by the loading rate dependency of the epoxy resin itself, but due to interfacial fracture. So we think mode 1 fracture toughness is not so sensitive with loading rates, not as much as fracture strength. I'd like to conclude by making the following points. The main this study evaluated and clarified loading rate dependency of mode 1 fracture characteristics of adhesive joints. The main findings of this study are as follows. This is all for my presentation. Thank you so much for your kind attention. Thank you.